Yeah, so hello student, welcome to today's lecture. So let us start today's lecture and very good morning. MA415 Algebra. Please pardon me because my laptop is very slow. So sometimes you can see that this is cutting. Okay. So algebra, and this is the lecture number I think 13. Okay. Now recall what we already discussed in last lecture. So we discuss about Sylow's theorems, right? Sylow's theorems. So what are the assumptions? So you have a finite groups that is given to you, and then it has three theorems. First theorem tells us that the Sylow subgroup of G is non-empty, right? P is a prime which divides the order of the group G. And Sylow subgroups is non-empty means there exists a subgroup of highest power of P which divides G, and also other P subgroups are also, yeah, so, and existence of all the P subgroups, yeah, so I'm not writing that, but that's also a part of this first theorem. Second theorem tells you that these P subgroups they are subset of this P Sylow subgroup. Okay, for some P Sylow subgroup. And third theorem, and also in particular the P Sylow subgroup of conjugate, all these P Sylow subgroup of conjugates. Okay, because when you choose a P Sylow subgroups, and that is also subgroup of a P Sylow subgroup, a subset of subgroup, and because of maximality, they has to be same kernel, right? So yeah, so and number three that counts that. Number of P Sylow subgroups. So in P, that number is congruent to 1 mod P, right? And also NP also divides the order of the group G. Okay, so there are many applications of the Sylow's theorems, um, and one of the most important applications of these to check a group is simple or not. So let me define what do you mean by a simple group. Simple group. Okay, so a group is oh, I told you this is sometimes it is annoying to me also because not a group is simple, or we say a group is simple group if it has exactly two normal subgroups. Okay, namely, what are those normal subgroups? Namely, this trivial group, the identity trivial like containing only one, and the full group. So let me write down a group G is called simple. Okay. So it has only two normal subgroups. Other than that, there cannot be any normal subgroups in between these two trivial normal subgroups. Okay. And classically, finding normal subgroups are very important. Actually, it has lots of applications uh, to check simplicity. And simplicity problem is related to problem of solvability, theory of equations. These are like classical problems. Okay, maybe I can teach you some by the later part of the course. Okay, so the Sylow's theorem is going to help us to check whether a group is simple or not, or what are the subgroups are there or not. So it's going to help us a lot. So let me just first start with a arbitrary group, say like what happen inside, say, a group of, say, order. So this product are two primes, say P and Q, and I can also assume that P is less than Q, right? Two primes, so one will be greater than another one. So let me assume that P is the smaller prime and Q is the bigger prime. For example, it can be 15, right? 3 into 5, or 21, 5 into 7, or 55, 5 into 11, something like that. Okay, so in this kind of group, what happened? So Sylow's theorem tells you immediately that that P Sylow subgroups is non-empty, and also Q Sylow subgroups. So here you have two primes, so you can talk about this. So let me assume that this is okay. So the G is the group of order PQ. Okay, and there. So let me assume that you have an element inside this, and you have another element inside this. This is P Sylow subgroup, and this Q Sylow subgroup. Okay. Then what can you say about then what can we say about Q first of all? So let me just think about Q without any assumption. Okay. So for Q, what do we know? We know that the number of Q Sylow subgroups, say in Q, it's kind of congruent to 1 mod Q, means it's kind of KQ plus 1 of this form, right? KQ plus 1, and it's also NQ also divides order of the group, which is nothing but P into Q, right? Sorry, this is NQ, not NP. This is NQ. Okay, so divides PQ, right? Now see that what are the possibilities? So if you see that if K, see, K can be what? K can be greater than equal to 0, right? So if K greater than 0 strictly, so here your K is option is that it can be greater than equal to 0. So it can be 0 or any positive integers. Now if I assume that if K is a strictly positive integer, then what happens? Then in Q is something which is strictly greater than Q, right? So in Q cannot divide Q, and also obviously, and Q is strictly greater than P, so in Q cannot divide these, and in Q uh, cannot divide P. Okay, and this gives you that NQ cannot divide PQ, because PQ is a prime number. If something divides PQ, then it must divide at least one of them, right? So there is a contradiction. So what is what is the conclusion? Conclusion is that Q must be equal to K must be equal to 0. So thus you can say that thus K equal to 0, and then what happen? Then NQ becomes 1, right? So 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 this Q is actually not a subgroup of G, right? Because we already showed that if there is a unique subgroup of some order, that must be a null subgroup, right? It's more than the actual normal. This is characteristic, but I'm interested in novelty to check something is simple or not, right? So I can easily tell that in this case, the Q Sylow subgroup is a normal subgroup, right? Yes. Now let us discuss about like the p-Sylow subgroup P. So for p-Sylow subgroup, what are the options? So NP is the number of p-Sylow subgroup. That is something again, some say k dash p plus 1 and k dash is greater than equal to 0, and also this NP divides PQ, right? Yeah, so this is given to us. So now you see, anyway, NP cannot divide P. I mean, there is no options unless it is 1, right? If k greater than 0, so NP cannot divide this. So, and P is a prime number, right? So this implies actually NP divides Q, right? So NP divides Q. So what does that mean? So NP equal to something. I mean, okay, 1 minute. So I should say either NP divides Q, or yeah. So there are two options. Either NP is so that means what? This means that either NP equal to 1 or Q, right? Because Q is a prime number, so NP has two options, either 1 or Q. Now I will give some nice situation to check what type of subgroups is this. That P subgroup. So P is the Sylow subgroup. Okay. Now, in particular, let me assume that say the two cases can be possible. So assume that your P does not divide Q minus 1. Okay. What does that mean? P does not divide Q minus 1 means this case, first case. If P does not divide Q minus 1, then NP has to be 1. NP cannot be Q. Okay. Because NP equal to Q means then NP equal to 1, right? In this case, as otherwise what happen? If NP not equal to 1, NP equal to Q, then so k dash p plus 1 has to be Q, and this implies that k dash p equal to Q minus 1, so P divides Q minus 1. But it is given that P does not divide Q minus 1, right? So thus NP equal to 1. So what does that mean? That means in this p-Sylow subgroup, it is also unique, and it is also normal subgroup to G, right? In this case, clear? So there are two options: either NP equal to 1, in that case p-Sylow subgroup is normal, or NP equal to Q. That I will come to that case also, obviously. Now let us discuss a little bit more about this case when NP is normal to G. Then what happens? Then you know that this Q is also normal subgroup to G, and cardinality of Q is a prime number, right? And that implies that Q is something, say, cyclic group, right? Because any group of polar prime cyclic, so it's generated by some single element X. Similarly, your P is also a normal subgroup in this case, okay, when NP equal to 1. And this cardinality of P is also a prime number, so P is also generated by a single element, say Y. Clear? So this is given to us, and you know also order of X equal to Q, order of Y equal to P. That's given to me, right? Now, the question is that what we can say about the the group G. Okay, so here let me just consider. You remember, if you have two set H and K, you know that the product is a subgroup. Is one is normal, right? Any one of these is normal. So here you know that both are normal. So now consider the subgroup PQ. Now PQ is a subgroup, and what is the order of the PQ? Order of the PQ is nothing but order of P, order of Q, and the order of P intersection Q. Right? The question is that what is C? We know that the numerator, this is P times Q. So what is this denominator? What is the order of the intersection of P and Q? And this is natural question to ask. Now what is the option? See, P and Q are distinct primes. So the intersection is always trivial. That means only identity belongs to that, right? So this order is 1. So this is PQ, and which is nothing but order of the whole group, right? So what does that mean? That means this PQ is nothing but G. G is actually this product PQ, or you can say isomorphic to PQ, no problem. But question is that what kind of group is this? Is this like abelian group, non-abelian, or something say cyclic group or not? So let me check it. Now probably you know the one theorem that when you have two elements and if they commute, then the order of the product is nothing but the right. So if I think you know these things, so let me again remind you. If you have two elements, say x and y belongs to G, such that xy equal to yx, then I'm assuming G is finite group. Okay, so G is finite group. I'm assuming order of xy equal to order of x into order of y. Okay, so this is I'm going to use, and for that let me show that these two x and y are actually commutes. So how you will prove that? So now recall that probably you remember that so whenever your group is okay, so I already proved that, right? So if G is acting on this all the left cosets of P by conjugation, okay, or rather I should yeah, okay. So if G is acting on yeah, so P was now subgroup to G. So you can write down a map from G cross P to P. And what is the action? So action is G dot some element P, sorry, GP going to G dot P, and that was GPG in the right by conjugation. And under these actions, remember you have a what should I say, group homomorphism from G to automorphism group of P, right? And the kernel is the centralizer of P, right? So we prove that G mod this centralizer of P in G, this is isomorphic to some subgroup of or a subgroup of this automorphism group of P, right? We already proved this thing, and this I'm going to use it to find out that whether they are commutes or not. Okay, so okay, so yeah, so what happened? Yeah, so now what is this? Okay, so I should okay. This is automorphism group of P. Yeah, so what is this group? So let us see. So what is automorphism group of P, right? This is the question, and that we already know. We have already discussed this problem. So that is nothing but I am asking what is automorphism group of Z naught PZ, right? Because P is cyclic group of order P, so this is nothing but Z naught PZ, and this is, we already know this isomorphic to Z naught PZ star, right? That co-prime classes modulo P, right? And hence we know the cardinality, right? Cardinality is P minus 1, right? So what does that mean? That means the order of G mod centralizer of P in G, the subgroup of this, so this divides this order of automorphism group of these, which is nothing but P minus 1, right? Yeah, so now check that. So what are the options? So this is see, order of group is G and centralizer of P in G is a subgroup. So these group, not subgroup obviously. What are the options of this order? So their options are 1, P or Q. There is no other options, right? Now we check that P also does not divide P minus 1 and Q also does not divide P minus 1, right? Q is bigger than P. So what are the options? So only option is that 1 divides that thing, right? So this gives you the option that this group has order equal to 1. Okay, so thus this group has order 1. Okay, so what does that mean? That means centralizer of P is nothing but the full group G, right? And what does that mean? That means, so centralizer of P in G, right? And so let me write down properly. So this is all those G belongs to G such that G P G inverse belongs to G P G inverse equal to P, right? For all P belongs to P, for every P belongs to P, right? So this is the meaning of centralizer, right? So centralizer of P, what does it do? It actually so one more minute. So P is a cyclic group, yeah. So what is given to me? It is given that P is a cyclic group denoted by Y, right? So for every such element of P, say centralizer is whole thing, right? Now centralizer equal to the full group G means what? That means um, this is for all G belongs to G, right? So what does that mean? That means every element of G commutes with every element. So this is the commutative relation, right? So in particular for Y belongs to P, क्या होगा? So for this G into Y equal to Y into G for all G belongs to G, right? So what does that mean? That means Y belongs to the center of the group. Y commutes with everything, right? So if Y belongs to center, then Y also commutes with X, right? So thus Yx equal to Xy. Y commutes with X, and thus their order is nothing but product of individual order, right? Clear? So what does that mean? That means you have an element in so thus this xy or yx, whatever you wrote, so or yx, yeah. So I mean this is also order of yx. You should not say the only order of xy. So yes. So this yx is an element of this pq, which is nothing but group G, okay, and order of this yx is same as the order of the group G, right? Both are PQ. This is P, this is Q, this is PQ, right? So what does that mean? That means G has a group element of order, which is order of the group G. So G must be cyclic. So G is a cyclic group, and G is cyclic group generated by this element XY. And we can also attempt to say that G is isomorphic to Z mod PQZ. Okay, isomorphic to, yeah. Clear? So in this case, you can actually classify properly how the group look like. Okay, and in the other case, you can also say that there are more than one. Okay, so in the other case, so in case 2, when this P divides Q minus 1. Okay, so when P divides Q minus 1, then what happened? Then this Q minus 1 equal to something, some K1 into P, and hence K1 P plus 1 equal to Q, right? Q. So so that divides that thing. So your NP is actually Q, more than one. So there are more than one Sylow subgroups. Okay, and now if there are more than one Sylow subgroups, then your P cannot be a normal subgroup. It's not normal subgroup to G in this case. Okay, because there are too many options, right? So the conjugates by G are not same, so they cannot be normal, right? Okay, so how can you say about these groups? So obviously, again, so in this case also, you have that group. We can also construct the group PQ. Now PQC, in any case, PQ is a group which is equal to G, because P intersection Q is empty values, right? This current is 1. Empty means, sorry, trivial. I mean trivial. The identity is there. Okay. So PQ is always there. Q is not subgroup. So PQ is always subgroup of G, and they have same kernel. So they are same, right? But here you check that here in this case G. So in this case G is not an abelian group. Check it. G is not abelian group. Okay, I can give you hints. So what you can check, you can find out. You can find out what is the centralizer of this capital Q in G, and you check that centralizer is full G if and only that group is abelian G. If it's not the full group G, then it's not abelian. You can check that. Okay. So this is the structure. So in group order PQ of the form P less than Q, then there will be Q Sylow subgroups, which is normal, and P Sylow subgroups may be normal, may not be normal. If it is normal, then G will be cyclic, and if it is not normal, if there are more than one options, then it is not even abelian. It becomes actually so this is, you can check at home. Okay, it's not normal. Okay, now so obviously there are so many other examples to check something is normal or not. So for example, I can ask you what about group of order, say 30. Okay, so for example, I'm asking whether a group order 30 is simple or not? Suppose this is my question. I want to know that if you have a group of order 30, is it a simple group? I mean, do you have a normal subgroup which is not trivial subgroup? Means not non-trivial normal subgroup, no, neither G nor the identity subgroup. Then what happens? So obviously you can again use Sylow's theorem. So you have a group G which is 30, right? So 30, sorry. So 30, how can you write on 30? So this is 2 into 3 into 5, right? This is the division of 30. So now let me check this. This is the highest prime P. So let me write down the P Sylow subgroup P, which is Sylow 5 of G. So this is the 5 Sylow subgroup. Okay, the P is 5 Sylow subgroup, and you choose another subgroup Q, which is a 3 Sylow subgroup of G. They exist, you know that, right? So now, what happens if one of those are either P or Q is normal? So if if either P or Q is normal, okay, then what happens? Then again this PQ is a subgroup of G of order 15, right? Because P5 and 3 are primes, right? I just proved that P and Q has to be empty intersection, right? I mean trivial intersections. Okay, so PQ is the subgroup of order 15, and hence PQ is normal subgroup to G. Why PQ is normal subgroup to G? Because the index of PQ in G is 2, and it is known that any index 2 subgroups is normal subgroup, right? Because in that case left courses and right courses become same. Okay, so in this case you are done actually if you have these things. If not, then what happened? Yeah, so yeah, so now one more thing I can say, that if P or Q are normal, any of the P or Q normal, then yeah, so let us assume, that at least one of P and Q are normal in G. Okay, and this is a subgroup of this is then PQ is not subgroup of G. Then we know that. Okay, so then you have PQ, which is not subgroup of G. But what about P? So issue that P is a subgroup of PQ, right? But PQ is a subgroup of G. PQ is a subgroup of G, and PQ has order 15, right? In this case, okay. So PQ is what? So that means, and also this 3 does not divide 5 minus 1, right? So what does that mean? That means PQ is cyclic. That also we know, right? Now in cyclic group, you have for every given order you have a unique normal subgroup, right? So what does that mean? That means P is a characteristic subgroup of PQ. Similarly, Q is a characteristic subgroup of PQ, right? That we already proved that if we have a unique subgroup of any order, that must be characteristic subgroup, right? So both are characteristic subgroup. Um, so what does that mean? That means now see P is characteristics in PQ and PQ is normal in G. So what does that mean? That means P is normal in G. Similarly, that this is the property you will this is one of the exercise, you will check it, okay? Similarly, Q is characteristic subgroup. This is you need to prove the exercise. This is simple proof actually. So characteristic subgroup have this nice property. Q is characteristic subgroup of PQ and PQ is normal. So characteristic subgroup of normal subgroup is normal. So this implies this Q is also normal subgroup. Okay, but normal subgroup of normal subgroup is normal subgroup of a normal group is not may not be normal, right? Okay, so in this case we get both Q and Q are actually normal in G, and so therefore we can assume that neither P-Sylow subgroup is P-Sylow subgroup is null. Okay, so what does we prove is we prove that your P and Q are normal, then everything happened, then both are normal actually, and everything happened. So this shows that if one of the P and Q normal to G, then uh, both are normal. Both are normal, right? So I can assume that neither 3-Sylow subgroup nor 5-Sylow subgroup are normal. Okay, so let us assume in the case uh, neither P nor Q is normal in G. Okay, so let us assume that. So this is not normal or that is normal. Then the question is that then can you find something interesting? Can you find still a simple normal subgroup of order 15 or not? Okay. So then what happens then? What is N5? So N5 uh, divides 2 into 3 into 5, right? But N5 cannot divide 5. So this means uh, N5 divides 6. Okay. And N5 is what? N5 is something of the form. So this implies N5 has to be 6 because N5 would be from something 5k1 plus 1, right? That is N5. So the option is that N5 has to 6, and there are 3 options, right? Other than 6, 1, 2, and 3, but 1, 2, and 3 are not possible. Similarly, what about for N3? So for N3 also, N3 is of the form 3k2 plus 1, and that should divide uh, 2 into 5, so which is that nothing but 10, right? And again it cannot be obviously you check so what are the options? The only options are N5, N3 can be N3 cannot be 1 because if N3 equal to 1 then Q equal to null subgroup, but I assume that is not normal, right? So only option is that 2, uh, 5 or 10, right? Or it can be 2, no, it cannot be 2 because this is of the form 3k1 plus 1, right? So 3k1 plus 1 cannot be, it never be 2. For a similar exam, similar design, it cannot be 5 right? Because it can be easy when k1 equal to 1, then this is 4, when equal to 2, then it is 7, right? So only option is 3, this 10. So here what you get in 3 equal to 10. Okay, clear? Okay, so now um, so 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 I have so what does that mean? I have 6 many Sylow P subgroup and 10 many 3 Sylow subgroup, right? Now you know that if you have a group a P Sylow subgroup of highest order, then whatever is the order of the element P, they must be belongs to this P Sylow subgroup, right? Some of the P Sylow subgroup, right? So what does that mean? So now you ask how many such element of order 5 are there, okay? So so let me just name it. So 6, right? So let me name it P1, P2, and then P6. There are 6, 5 Sylow subgroups. Sylow. Ah, so 5 Sylow subgroups. Okay, are there. And order of these 5 Sylow subgroups are what? They are all 5, right? And so in P1 there are 5 see these are all cyclic group order 5, and except identity all the element have order 5. So there are 4 element of order 5, there are 4 element of order 5, right? And so on, the 4 element of order 5. So thus altogether how many elements we will have? So there are total 24 elements of order 5 are there in G, right? Clear? If it is this, you know, the factor subgroup is not normal, it must be there must be 6 many such subgroups there, and you have 24 elements over 5, right? Now similarly you check that okay, so similarly what you can check, about that 3 Sylow subgroup Q1, Q2, and there are 10 many, right? Q10, and there are 3 Sylow subgroup. Sylow uh, subgroup. Okay, and 3 Sylow subgroup means they are all cyclic group order 3, and except identity all the group of order 2. So you have order 3. So you have 2 elements of order 3, here also 2 elements of order 3, and so on. So total 2 into 10. So 2 into 10, which is nothing but 20 elements of order 2 are there in G. Now this is a contradiction. Why? Then what happens? Then number of element will be order 2. Number will be P is about 24 plus here 20 plus at least identity is there, right? So number of elements of the group, this will be 45, right? 45 is now bigger than 30. G has 30 elements only. So this cannot be possible, right? So what does that mean? That means both P and Q, what I assume that they cannot be normal is not possible. So thus at least one of P and Q is normal, and hence PQ is the normal subgroup of G of order 15. So G is not simple. G is simple. G is not simple. G is not simple. You have a non-trivial subgroup of order which is in between 1 and 50 or 30, right? Yeah. So similarly, you can check what about group of order, say 30, or sorry, group of order something. Whatever order you can ask, 36, 44, and these things. So the interesting part is that up to so this Z mod Z mod PZ, whenever P is a prime number, so this is one class P prime. So this class actually contains all simple groups. Okay. Now you can also check, this is kind of homework, that the only uh, groups um, only simple groups up to order 60, I mean up to order 60 before 60, I mean to say up to order less than 60 are this Z mod PZ for some prime. Okay, with P less than 60. These are the only simple groups up to order 60. Now you check it, this is homework, that if you choose any group other than Z mod PZ of order up to 60, they cannot be simple group. Yeah, so there must be a normal subgroup, which is not the trivial normal subgroup. Okay, so this is interesting exercise, you can do it. So the interesting example comes at the group of order 60, and in this case you can check that you have a group of order 60 which is simple, and which is not equal to, I mean is not the of this form. Okay, and that is called the alternating group of order 60, and this is A5. So this problem is, maybe I can discuss in next day. Okay, so let me just stop here for today's lecture.